tells me it's live. It doesn't tell me it's live here. I don't want to play all you crazy bugger. I just want to see what's live. All right, I don't understand. Responding. Already error you to open studio. I don't want to start recording. Stop that. What is studio mode? What good is that to me? Oh, I see. Okay. It says gives me an error. Why? Why? I have no idea. Come on. Damn it. Stupid thing. That's Facebook. That's YouTube. I don't care about that. Get out of there. Okay. So it tells me, here it is, but it's not error. Oh, I see. So it's not, something's not happening. Why? Switch account? No. Select stream. Refresh. So I don't want to go to here. And let's see what we're looking at. Oh, okay, good. So if I do this, tells me here it is, but it's I am now. Oh, I see. So it's not, something's not happening. Why? Switch account? No. Select stream. Refresh. Here. And let's see what we're looking at. Oh. Oh, okay, good. So if I do this, and I don't know where my camera is. Oh, it's still there anyways. It'll be there the whole time. Yeah. Where my camera is. Oh, it's still there anyways. It'll be there the whole time.
Okay. It looks like we are working. But there's a serious delay. So, again, I'm probably talking to myself. I'm just busy trying to test some software to see if I can share my screen, and then I can try to do my videos a little differently. And more importantly, we want to start thinking of live streaming, as I said in the one I did yesterday, which was far too long for a test. What you can see on the screen now is an image of the 1720 masers that we're monitoring at Hartreo. The image, if I turn everything off or get it off the screen, here is an image of Hartreo taken with the moon, as you can see through the tripod holding the subreflector at the top. And this is a great place to stand, by the way, when you want to do surfing. You stand up here at the very top, and the wind, even when it's at zenith, it actually shakes a little bit, and you got to keep your balance without falling off. And of course, the falling off part is pretty bad because that's about 30 odd feet right there from the top to the dish. So that's kind of cool. But anyways, that's Hartreel's telescope. That's a 26-meter radio telescope in South Africa. Now, going back to the image you can see on the data here, what I'm actually trying to show you, just as a quick test, is that we see all, this is, first off, let me say this, that we're getting my glasses on, I can't read a damn thing without them, but you can see we're getting fairly high resolution in terms of velocity because we're fitting Gaussians to it, and more importantly, that the spectra of the 1720 masers is really only a 1 or 2 feature component. So the total power spectrum and velocity is only made up of 1 or 2 maser spots, basically, in both R and L. Anyways, and you can see here that the red is the RCP polarization, and of course the blue is the LCP. And we can see that there's a turnover occurring here, and that's why I've got it marked with this square line, and this is what I've been busy looking at for some time. If I wanted to show you, let me give you another transition. Let's look at lips aren't working. Let's look at 1667. Okay, this is brutal. Man, this is crazy. There's a great picture I want to show you in here, if I can find it. I got all sorts of graphs here, all sorts of everything. If you can see here, again, you can see this, what looks like a turnover, although it's in the noise. Clearly it's in the noise, okay? Now this isn't the image I was wanting to show you. I don't know where the heck the image is. Where the heck is it? What am I thinking about? I thought it was 1667. And I don't think it is 1667 now. Okay, that's probably why. Let me just check something here. Yes, okay, so the problem here is I'm missing, this is old. I'm on my another computer and I'm looking at an old data set and I'm only seeing up to the fall of 2022. So there's the reason why I'm not seeing the graph as nicely as I'd like. Anyways, but you do get some idea that there might be a turnover here, and then there's, as you can see, it's here, it's about 77. So here it's also at about 77. So you have two different transitions where we're seeing a line basically turning over. And the interesting part about these particular feature, or this feature rather, is that and just for people who are watching this who aren't astronomers, this is really what I do all day, is look at graphs like this. So first I have to process data, and then that data, it comes in as raw. It comes in as basically raw data where I have to take away the band pass, and I have to shift and fold and all sorts of other crazy things, calibrate and so on, do position checks. If I would do it, ground state OH, I don't do position checking because the beam of the telescope at Hartreo is so large, a half degree, that it's the correction factor is so small it's not relevant. At least not in terms of flux, but in velocity, extremely relevant. That's another story. Anyways, long and short of the story is I've got one transition at 1720, and the smaller one you see here, and I'm pointing and you probably can't see it. What I'm pointing at, let me use my cursor, undulation over about 5,000 days, which is really kind of cool. And let me see if I can show you some other stuff anyways. We'll go out and I'll try another image here. Another transition rather. And this is the 1665. So this is all hydroxyl masers, hydroxyl maser data. And the thing to note when I show you this is the resolution is really quite impressive. And we get that by fitting Gaussians to it. So if I was just looking at velocity channels, which is the typical way of looking at time series and whatnot as it relates to masers. We make a dynamic spectrum, we do a cut across it, a horizontal cut, and from that you get a time series for flux for a given velocity, okay, or something like that. And you can do some other stuff. Here you can see 1665, and at about the same time, you can see the turnover. So now you can see the turnover. And just as a matter of interest, I'm trying to, you can see the top is RCP and the bottom is LCP, or I can't remember which one's which, but I buggered it all up because of all the colors and that. Anyways, way too confusing. But the point is, I'm trying to show you that in 3 transitions, we're seeing a turnover at about the same place. Now let me get all this off the screen because it's all a bit confusing, and I don't want to do that. So what I'm trying to say here is that if you have 3 different transitions, the masers aren't co-propagating. They're not co-located, at least not the 1720 with the others. And as a result of this fact, it's got to be something generalized. In other words, what's causing this is either instrumental, it's either in the telescope, it's something about NGC 6334I-MM3, a very long-winded name for what I call KITTI. Well, actually, KITTI is the new star forming region, which is MM1. This is the old area where a massive star has been born and has been studied for a very long time, as you can see from my monitoring data. Anyways, and when you look at this data, you start seeing these little humps and bumps in it, and they tend to follow. The LCP and the RCP tend to follow each other. And that is likely the Earth going around the sun. So what happens is we're getting such accuracy now that the velocity calibration is not something anybody worries about at in single dish telescopes, simply because we've never had the velocity sensitivity to actually see the Earth going around the sun. Well, we can see that, but what I mean by that is, I gotta turn the sound off, it's driving me nuts. No. Okay, so what I'm basically trying to get is this. So the Earth goes around the sun, which of course the observatory, Hartreo, is attached to the Earth, obviously. And it goes around the sun. The sun goes around the local standard of rest of stars, okay? And that local standard of rest we do a correction for that when we observe, because we know that the Earth is moving, therefore we have to correct the velocity, the Doppler shift of our spectrum, of our spectral line, in this case, 1.72 gigahertz on your radio dial. We have to correct for the fact that the Earth is moving, or is going around the sun. So the object's not moving, the Earth is moving. Anyways, that correction, interestingly, is proportionate. That correction is always to the beam center of the telescope. Now, on a half-degree beam, you could have sources spread, or you could have sources that are 20 arc minutes apart, and that would be a significant velocity drift as a result that has to be corrected. So if it's not at the beam center, and I see this in other data, I don't have the images, or do I, that I can show you. Let's see if I can find some early images of dynamic spectra that show what the heck I'm talking about, because my lips are moving and I'm just saying crap for nothing. Where the heck are we? Where are we? I got lots of, way too much data here. Way too much data. Way too much. Alrighty. Proper motion, velocity drift. Let's see if we got something in here. Probably not. No, it's all sorts of funny things. Let's just go back to where I was. Let's go to images, and let's see if I can find, oh, I think I got something. Good, okay, here we go. So, this is a perfect way of showing to you what I'm talking about. So this is dynamic spectra. So rather than just looking at, here I'm just looking at one particular feature as it relates to velocity. And in here you can see the velocity of all the masers, and the contours, or the colors in this case, represent the strength of the maser itself, 0 to 600 Janskis, the 600 Jansky source being the brightest right here in the middle. Anyways, this wiggly line here, this undulation is sinusoidal, and it has a period of 365.24 whatever days, and that of course is the result of the Earth going around the sun and the sun going around the local standard of stars. So that undulation I should be able to see in this data if I get high enough resolution. I see it here simply because the source interfering it with the ones I'm interested in, which is the flaring that went on in this area here, is actually about 20 arc minutes away. And so if it's 20 arc minutes away, there's a proportionality of the size of the undulation, in other words, the amplitude of the undulation, okay, to the beam center, and it's directly proportional. So if it's 20 arc minutes away, it's 0.2 arc seconds, clearly visible. 0.2 arc seconds, the velocity resolution here is 0.05 kilometers per second. I keep saying arc seconds, kilometers per second, sorry. So my velocity resolution is 0.06 for each channel, and there's 512 channels, whatever. Anyways, in the spectra, okay? So you're gonna see a change of 0.2 very easily, because that's 4, 5, 6 channels, and you can see that undulation here. Now, but of course, if you're much closer to the beam center, that undulation becomes very small. We're talking smaller than the velocity resolution that we're seeing here, and you no longer see that undulation. Well, as you can see here, I'm starting to see it again. Why? Because I'm fitting Gaussians, and a Gaussian uses, rather than just using channels, which is what I'm using here to plot data, I'm actually fitting to the spectra a Gaussian which uses the entire shape of the spectrum, and that gives you a much more accurate velocity peak. And with that, we're able to start seeing the small differences off the beam center. And these differences here may only be literally an arc minute in a 30 arc minute beam. So it will not show up in flux density at all, because the correction at 1660 at 1720 in a 30 arc minute beam would be of the order of less than 1% correction. So you won't even notice it, because the error, my pointing error is always of the order, or my calibration error is always of the order of 2 to 5% in this data. So I'm never going to see that in flux. But because my velocity is very accurate, the peaks, I can actually see that. And so we can start studying what the tendency of the velocity is. So when I originally did a paper on velocity drift of this particular source, NGC, we actually, all I did was use the channel peaks variation. So that gives you a generalized view of a lot of maser points. And it's not very accurate. It's literally at the resolution of the channel width, okay, which is 0.05 kilometers per second, or whatever the hell I'm using. Whereas when you start fitting the Gaussians, as I said, you're getting down to 0.00, you're getting down to, what does it work out to? Anywhere from 5 to 0.5 kilometers per second. Now I'm getting down to 5 to 0.5 meters per second. So an improvement of 10 to 100 in velocity resolution. And now, if a source is even an arc minute away from the beam center, I can see it. So that's the answer to the story, right? And as I said, there's a proportionality to that, and the undulation becomes very small, and you start seeing that undulation. And that's what that likely is. Having said that, it could be something totally different. If that undulation does not have a period of 365, well, then this is a different ballgame. So anyways, back to this thing. This is a dynamic spectra of the Ellen RCP at 1665. You see these beautiful features here are actually from the source NGC 6334B, not F or I. There's some nomenclature screwing around because people in the Southern Hemisphere use one catalog, probably the Australian catalog, and we use F as its designation, whereas those in the Northern Hemisphere typically use I based on the VLA observations done back in the early 80s. So just as a matter of interest, that's where the I and the F come from, just to make it confusing for all of us. Anyways, so this is a dynamic spectra. We can see the source B here, and all the rest of the masers, and 65 masers, turned on. It's kind of interesting. You can see that there's some slight mazing activity here, and that's another feature that's probably from B. So it's interfering. So you have to start disentangling all of these things. And the beauty of doing high-resolution Gaussian fitting is maybe we can. So how long have I been talking for now? I don't know. Anyways, so let me just end by saying this. This test seems to have worked. That's the most important part. We can get very high-resolution imaging, and with that, we can start looking for some unique properties in the velocity rather than simply the flux regime. And this is one of the biases that we live with. Most of my astronomy friends are focused very heavily on the flux, largely because it's the most obvious. We can see it. And it takes a hell of a lot of work to get to this level here, I can assure you. And then some of this may not be believable. And they literally are sitting on each other, almost the same velocity, and only slightly separated, or rather they're at the same velocity, one bigger, one brighter or stronger than the other. It gets lost. So that stuff starts getting lost, and so people don't worry about it. So it's difficult to disentangle. And some of the work I'm doing on now is to do precisely that, and hopefully I'll be able to. Anyways, I'm going to finish now because this seems to have worked. So I thank you for putting up with this annoyance. I'm working on two computers, so bear with me here while I'm typing some stuff here. It seems to work. I am typing and sending out to the